All right.
Looks good.
Okay, hello everyone. Welcome to another online edition of Astronomy on Tap. My name is Dr. Andres Plazas Malagon. I'm a researcher at Princeton University, and my co-organizer, Dr. Alexander Havex from the Washington University in St. Louis. We are very happy to bring you this online edition of Astronomy on Tap. And before we continue to our talks, we would like to thank our sponsors. This is an event that is supported by the Department of Physics of Washington University in St. Louis, by the Academy of Science of St. Louis, by the JPL Solar System Ambassadors Outreach Program, by the McDonnell Center for the Space Sciences, and by Urban Chestnut Brewing Company in the city of St. Louis, where we usually have our events when there is not a pandemic. So today it is my pleasure to bring you two friends of mine and colleagues from projects such as the Dark Energy Survey, and they're going to talk about cosmology. And our first speaker tonight is going to be Dr. Rutuparna Das. So Dr. Das is an astrophysicist and science communicator, and she spends her time learning about the universe and sharing its wonders with everyone around her. After going to undergrad at MIT, she completed her PhD at the University of Michigan, where she primarily worked on the Dark Energy Survey, as I mentioned. She now works at the Center for Astrophysics, Harvard and Smithsonian, bringing multi-wavelength astrophysics to the community through NASA's Universe of Learning, and continuing her research, which she will talk about today. So, Dr. Das, thank you very much. And please, let's give it away. All right. So just one reminder, we will encourage everyone who is watching us to ask all the questions during the talk in the chat, and between the two talks, we'll be happy to take your questions and pass them along to our speakers.
Thank you, Andres. Sorry, I started and realized I was muted. So thank you for that introduction. So a long, long time ago, in galaxies far, far away, light was emitted. These pinpricks of light left these galaxies that are, millions to billions of light years away from us. These pinpricks of light traveled through space, tossed and turned and buffeted about by everything that they found in their path, until finally they fell through our atmosphere to land on our telescope on a mountaintop in Chile. Hi, I'm Rutu Das. I'm an observational cosmologist and science communicator at the Center for Astrophysics at Harvard and Smithsonian. And today, I'm going to tell you how those twists and turns and movements of light can tell us about weighing our universe. So I said I'm a cosmologist, right? So what is cosmology? It's the study of the universe, how it began, what it's made of, how it's changing over time, and ultimately what's going to happen to it in the future. So I imagine almost all of you, if not all, would have heard of the Big Bang. So the universe grew very quickly, got very big really fast, and continues to grow to this day. Great. I am willing to bet, or at least hoping, that fewer of you have heard of the Big Crunch. And you'll see why in a second. So the universe expanded from the Big Bang, continues to expand to this day. And scientists observed this expansion in early last century. So of course, scientists being scientists were like, well, okay, universe is expanding. It must be leftovers from the Big Bang, but gravity exists. The same gravity that if I throw this apple into the air, brings it right back down to me. That same gravity holds us to the Earth, pulls the Earth towards the sun towards the center of our galaxy, and pulls every object in the universe towards every other object. So they're like, okay, universe is expanding outwards, but gravity is pulling inwards. which means that at some point, this pull of gravity should make the universe slow down. And at some point, the universe should stop. And then, because of gravity, start falling inwards and collapse into a big crunch. Now, scientists, being scientists, needed to know, when was this going to happen? When will the universe end? Because, we can't just be satisfied knowing that, there's going to be a big crunch and whatnot. So when is it going to end? Dun, dun, dun. Lots of people try to find out, because when you have more people working on something and, people do independent research on the same things, if multiple people find the same thing in many different ways, that means we can have more confidence that that's correct. So lots of people were looking at the sky, trying to figure out when the universe was going to start collapsing. And in the late 1990s, two groups independently working found, to their utter astonishment, that somehow, inexplicably, incredibly, the universe was accelerating. Now, this made no sense whatsoever. This was ridiculous. How could this happen? Because this is so crazy. This is like if I took this apple and I threw this up, and instead of coming back to me, it got faster and faster and flew off into space. Now, I have my apples, so clearly that didn't happen. So what was going on? This was mind-boggling. The astronomy community was in shock. And then we dusted ourselves off and we're like, okay, great. Something weird is going on. We have to figure out what it is. Where did we go wrong? What are we missing? Because the universe is not wrong. The universe just is. So if our idea of what the universe should be doing doesn't match what we actually see the universe doing, then that means we are wrong. The universe is always correct. So then we set about trying to figure out what was going on. Why were we wrong? What did we miss? Well, so the only thing we really knew about it is that there is some form of energy that's causing the universe to get bigger and bigger, faster and faster. We don't really know what it is. We don't know much about it. We can't see it. And so we very aptly named it dark energy. Dark energy is a name given to whatever is causing our universe to accelerate, seemingly inexplicably, before we put this dark energy idea in there. So we have lots of questions about dark energy, like what it is, what's the source of this energy, what's causing the universe to do this. I leave that to the theorists because I can't do that much math. But my job is to figure out how much dark energy there is and how it's changing over time. Because if there isn't enough dark energy and gravity can overpower dark energy, then the universe would end in a big crunch. But if there is a lot of dark energy and it overpowers gravity, then the universe is just going to continue to grow and accelerate until everything flies apart. And if, for those of you who are keeping track of your big endings of the universe, that's known as the Big Rip, that idea. So we're trying to find out what's going on with dark energy to learn about what our universe is going to do in the future. There are many ways. So how do we learn about dark energy? How do we learn about the universe? Well, I said I'm an observational cosmologist, right? So that means I learn about the universe by looking at it. And there are many things in the universe that we can look at to learn about dark energy. And the Dark Energy Survey, which I work on with Amy, who's going to speak after me, and Andres, who introduced me. The Dark Energy Survey uses several different ways of measuring this, but I'm going to talk about one in particular called clusters of galaxies. Now, galaxy clusters are exactly what they sound like. They are a bunch of galaxies that are held together by gravity and are sort of, going around each other. And these are the most massive objects on the, I was going to say these are the most massive objects on the planet, but clearly they're not. These are the most massive gravitationally bound objects in the universe. These are the biggest things that we can look up there and be like, oh, hey, there's one, but they're held together by gravity. And they are so massive that they have a really, really strong gravitational field. Their gravitational field is so strong that anything passing by, a stray galaxy here, another stray galaxy there, they get attracted towards the cluster and they fall in. And this makes the galaxy cluster grow over time. However, dark energy is making things move away from each other, right? So that actually hinders the growth of these clusters. Because on one hand, there's gravity pulling things inwards, trying to pull, all the stray galaxies nearby into the cluster. And there's dark energy causing things to move further and further away from each other. So galaxy clusters grow at a slower rate than they would grow if dark energy did not exist. So this is great, because then we can ask the question, hey, so if we can just find out how galaxy clusters grow over time, we can ask the question of how much dark energy does there have to be for the clusters to grow at the rate at which they do? So, okay, that's all fine and good. Now, how do we find out how much a galaxy cluster weighs? So this is, beautiful cluster, lots of galaxies. And maybe you can say, okay, we can count the number of galaxies and we sort of know how much galaxies are supposed to weigh. And we can kind of estimate how much mass there's gonna be in here. That's great, except all of these galaxies that you can see, all of these, all the yellow ones that are part of this cluster, all of them that you can see only make up 1% of the mass of this cluster. 1 measly percent. That's okay, we want to learn about the whole cluster. 1% it could be the margin of error. It doesn't really tell us that much. So how can we learn about the whole cluster? Well, here's where we bring in something that astrophysicists like to call multi-wavelength astrophysics. I'm going to take a little detour here. Okay, we're going to leave clusters for a second and come back to our own solar system. So this is our sun. Many of you may have seen this picture. This is what our sun would look like to our eyes if we could get past all the, blindingness and look at it. And it looks fairly boring, a couple sunspots here, not much going on. However, if we look at our sun in infrared light, this is the kind of light that night vision goggles see in, it's heat basically. We see that its surface isn't as smooth. There's quite a lot more going on. Some unevenness, bigger sunspots. It's not what we thought from visible light. Then we look at ultraviolet light coming from the sun and whoa, we see more. All of these swirls are like magnetic fields twisting about the sun. And we had no idea of this when we looked at it with just visible light. Add in X-ray light and you see even more violent stuff going on the sun. X-rays usually show some of the most energetic events in the universe. So you've got flares and magnetic field tangles and whatnot going on. So using different parts of the electromagnetic spectrum, we can see different aspects of what's going on in the sun. Each of the pizza slices you see here are basically in a different type of light. And they all show us different details about what's going on that surface. So in the same way, we use different types of light to look at galaxy clusters. Now, this is visible light. If we could get close enough to a cluster, this is to this cluster, I guess, this is what it would look like. However, as I said, this is just 1% of the cluster's mass. So we look at it in X-rays and we see this blob. What we're actually seeing here is the intracluster medium. That's this super hot gas that's permeating the entire cluster. And that's so hot that it keeps emitting X-rays. And that's what we're seeing here. And, we can by the size of the blob and by how bright the X-rays are, we can make an estimate of, okay, there should be this much gas and maybe, then we can, and we know it's mostly hydrogen. So, okay, we can be this is how much the cluster should weigh. Great. So, we add that, we have our galaxies, we put X-ray and visible light together. Great. So, that should give us the cluster mass, right? Well, all this gas and the galaxies together are still only 10% of the cluster's mass. 10%. We are missing so much of the cluster. And the reason we can't see it is because that stuff is dark matter. It's matter that does not interact with light. It has gravity, but we can't see it with any kind of light. We can't see it with visible or X-ray or optical or an ultraviolet or gamma rays or anything. So how do we go about actually measuring the mass of a full galaxy cluster? Well, there are some indirect ways. Like I mentioned, we can count the number of galaxies. And we can say that, there is a relationship between the number of galaxies and how big a cluster actually is, how massive a cluster is. And, we're still working on figuring out that relation exactly, but we can get an approximation. It's not that exact, but we can get an approximation. Also, using X-rays, we can get an approximation because we can say that, for the cluster to have this much gas, there's also some sort of relationship between how much mass it should have, and we can make estimates. There's another way. If you guys follow Astronomy on Tap St. Louis continuously, then you would have heard about the cosmic microwave background in the previous talk. It is this microwave radiation backdrop to our visible universe. And basically, when we can observe electrons coming from that background, passing through clusters to us, and the clusters sort of mess with the electrons, and the more mass a cluster has, the more it messes with the electrons. So if we can figure out how much a cluster is messing with the electrons, we can be like, okay, it's probably about this massive. So that's all great, but these are still all estimates. And also to figure out the relation between, the number of clusters and the mass, we still need a direct way to figure out how massive a cluster is. So now we look at direct methods. Again, we go back to the galaxies ones. One way of doing it, except instead of counting them this time, what we're doing is we are looking at how they're moving. Now, things orbit other things because those other things have gravity, right? You have something with a strong gravity, then you have things orbiting it. The stronger the gravity in the center, the more mass in the center, the faster things are going to orbit. So by looking at how quickly the galaxies on the outsides of these clusters are orbiting, we can find out how much mass there has to be at the center. Remember, this is all dark matter. We can't see it. So we have to see how it affects things around it. And because dark matter has gravity, it will affect how quickly things are orbiting around it. So that's one way. We can also do a more direct way with the gas measurement. So the interesting thing is all this super hot gas in the cluster that we're looking at in X-rays over here in the blue. It's, by the way, just colored blue. X-rays aren't actually blue. X-rays can't be seen by the eye. We just colored it blue so you can see the shape. All these X-rays here, all this gas is actually putting a lot of pressure outwards. And gravity, of course, is pulling the cluster inwards. And what happens is that for the cluster to maintain its shape, that outward pressure from the gas has to balance the gravity. So we can say that, okay, given that the cluster is maintaining its shape, how much gravity does there have to be to balance this gas pressure outwards? And we know the gas pressure outwards because we can see the X-rays. So that's one way. Except that depends on assuming that a cluster is maintaining its shape, which is not always true. So my favorite way is using weak gravitational lensing. Now, I'm assuming that many of you have heard of how black holes are so massive and have such great gravitational fields that even light cannot escape them. Well, clusters also have strong gravitational fields. Light can escape clusters, obviously, because otherwise we wouldn't be able to see these beautiful galaxies. But as light passes by clusters, the gravitational field bends the light. And that tells us a lot. So here's sort of a diagram. If this is a galaxy cluster here, I think you can all see my mouse, this gray blob over here is a galaxy cluster. These are galaxies in the background, behind the cluster relative to us. We're sort of in the front here looking. So these are galaxies behind the cluster. And as they pass by, their light is sort of bent by the cluster until they reach us and are sort of aligned, or they look aligned. In reality, they're not. So here's another way of looking at it. This is like let's say this is galaxies behind a cluster. They're randomly oriented in the sky, you know, pointing every which way. But if there's a cluster in front, they sort of start to line up tangentially around the cluster. Now, this is really, really exaggerated. It's called weak gravitational lensing for a reason, because you can't actually see this effect with the naked eye. You have to actually measure thousands to tens of thousands of galaxies and average all of their shapes, and you're going to find that there's some sort of like ring-like lining up, alignment forming. And the more mass a cluster has, the more it's going to distort the light from the galaxies behind. So if we can measure this light distortment, we can tell how massive a cluster is. So where does that bring us? We use gravitational lensing to figure out how massive a cluster is. We use that to figure out how clusters are growing over time. We then look at the tug of war between gravity and dark energy to figure out how much dark energy there has to be for the cluster to grow at the rate that it is, for the clusters to grow at the rate that they are. And then we can use that to figure out what the fate of our universe will be. This process, of course, takes a lot of work. Every single step of this process has tens to hundreds of people working on it at any given time. Astronomy, you know, used to be that like people thought astronomy was just a lone person on a mount, or a lone man on a mountaintop, putting their eye to the telescope, looking out at the sky. That was like Tycho Brahe, I think in the 1500s. He still worked with people, but yes, he was like, you know, looking out through a telescope and writing down one by one. As I just said, we need to look at tens of thousands of galaxies at the very least. So you can't do that by yourself. And this is a picture of our collaboration, the Dark Energy Survey. This is a really, really old picture, actually. This is from 2015. But yeah, we have this is a small part of, this is like a chunk of the collaboration. We have like 400 to 500 people, I want to say now, working on doing every part of this so that ultimately we can figure out what's going on with our universe. We still get mountaintop with a telescope. It's beautiful skies up there down in Chile. And this is our telescope. It's pretty giant. If you stand, you're like, you know, a tiny little pinprick down here. This is the detector, which is sitting in this part of the telescope. And actually, it doesn't look that big in the photo, but the height of it is about the height of a preschooler. So you can imagine it's pretty huge. Yeah, so we all work together to use that telescope. Dark Energy Survey built that camera that went on the telescope, and to look at this patch of sky, this like outline is showing you the entire patch of sky. From this, we'll find, you know, hundreds of thousands of galaxy clusters and millions of galaxies to use in our measurements. And we do this all together because you know, we have to work together. We have 7 different countries involved, last I checked, in the Americas, Europe, Australia. Unfortunately, I guess this image can't show the whole world, but this is also just a random image and not exactly, you know, the places that are involved in this. But yeah, you have to work as a group, and not just on the ground. I currently work with Chandra, which is an X-ray telescope in space that also took hundreds to thousands of people, decades to design and build and send into space and run and now work with the data. So it truly takes a planet to search the universe. Thank you.
Thank you so much, Rutu. That was a great talk. So now we're going to see if we have some questions in the chat. Let's see. Okay, we have people from Chile. We have people from North Haven, Connecticut, from the Bay Area. Oh, welcome everyone. And we have our first question here from Fred. How do we know the X-ray blob is gas?
How do we know the X-ray blob is gas? We actually can do spectroscopy. So the things that I showed you are all photos, but we can also look at individual, like, we can look at the exact wavelengths of the light that's coming to us from those blobs, and different elements emit different wavelengths of light. So by looking at those wavelengths, we can actually tell what elements are up there, and it's mostly hydrogen. And it's so hot, like it's mostly hydrogen gas.
All right, thanks. We have another question from Bernardita, and she's telling us, have you ever visited Chile?
Oh yes, that was one of my favorite parts. So Dark Energy Survey finished its operations. Wow, the years. Last year has been really weird. So the years are melding together. Hey, when it was like not last year before or something like that.
Something like that. Yeah,
Pandemic's
a
thrown us
year
all
ago.
off. But fairly recently it ended operations. But I have been there 5 times. So every year we had about half the year or more than half the year where we were taking observations, and of that group we would take turns going down there, and I went there like for years 1 through 5 of observation, and it's beautiful. I was like, I can't believe this is my job to stand here and, make sure the telescope's operating. And it actually says in part of the like list of instructions, the things you're supposed to do is go outside, stay there for 10 minutes, let your eyes adjust to the dark, look up, come back and report on the weather. And I'm like, okay, my job is to look up at the sky. This is awesome.
That's right. Yes, I remember that. I had a chance to go there, and they had that in the instructions. I'm glad they tell you, because sometimes you get very nervous just looking at all the instructions and you don't want to break anything, but it's good to take a break and then go outside, and it's like a sky you've never seen before. Do you have any particular memory from your trips in Chile? Or this is a question from me, like, what's your maybe best memory
Um,
or
Lots
something
of
you want to share with us?
I actually, so one of the things is the people there are so nice. So I mean, I spent most of my time on the mountaintop. So I got to know like the people of the observatory. They're so friendly and so helpful. And they have so many scientists coming year after year, but they remember you. Like I am like one person who showed up throughout an entire year. I go back the next year, they remembered who I was. And they're very helpful. They're the reason our telescope doesn't break, by the way. We like figure out where to point in the sky and stuff, but they make sure things don't break. And just the staff there, they have like an entire staff to take care of us, like to cook and everything. Everybody's just very nice. And, they all sort of celebrate in the stuff going on there. Sometimes we have to be there to observe. Like I've been there at Christmas once. I know people have been there at New Year's, and we all sort of celebrate. It's we're there, but it's like a large, big, happy astronomy family.
Yes, I remember the food as well. Especially they accommodated our dietary restrictions. The
Very
king
nicely,
of
yes.
empanadas, says Bernardita. And Fred also says, thank you so much for a very interesting presentation. So
For listening.
I don't think we have any more questions. So I want to once again thank you, Rutu. And I want to welcome our next speaker, Dr. Amy Choi. So Dr. Choi did her undergrad at the University of Chicago. She spent 1 year at Fermilab in the Chicago suburbs. And I missed what I was reading. There you go. On a neutrino oscillating experiment. So she did her PhD at the University of California, Davis, and then after that she did a postdoctoral. She had a postdoc at the University of Edinburgh, and now she's doing a second postdoc at the Ohio State University, where she is currently based. She is a member of several large international science collaborations, such as the Dark Energy Survey, and some of them are shared with Rutu, as Rutu just told us. And she will talk about these collaborations in her talk. So welcome, Dr. Choi, and please go ahead.
Thanks, Andres and Alex, for facilitating, and good evening, everyone. Thanks also to Rutu for that amazing talk. I think it's a great lead in to the things that I would like to talk about. So I've titled the talk Seeing the Dark Universe. So that's going to be a focus on a little bit more on dark matter and gravitational lensing. And what we see on this first slide is a picture of the sky taken from the Gaia Space Telescope. And the Gaia Space Telescope has taken very accurate 3D position information of, I think, over 1 billion stars. And so in this picture, which is kind of a warp distortion, so you might be able to see that the Milky Way here is now in the shape very much similar to the Gateway Arch. And then there are 2 little blobs in the bottom. So these are the Large Magellanic Cloud and the Small Magellanic Cloud. And what's appearing and disappearing right here in the center is you might recognize the footprint from the dark energy survey. And I'm going to say that this is a map of the dark matter. And hopefully throughout this talk, you'll get a sense of how we were able to make this map. Okay, so Rutu already gave a really great introduction to some of these topics, but I always like to start by thinking about where we are and how that is related to the rest of the universe. So we're here on Earth, we're orbiting around the sun, and then the sun is one of many, many, many stars in the Milky Way galaxy. And this picture here is an artist's representation. And so the sun is orbiting around the Milky Way. It's bound by gravity, another thing that Rutu mentioned. And then the Milky Way is actually not alone. It's part of what we call the local group. So there are several galaxies that are bound together by gravity that happen to be very close together in space. And so here you can see again the Large and Small Magellanic Clouds, and then our neighbor galaxy, the Andromeda Galaxy, and then some other smaller galaxies. Rutu also talked about galaxy clusters. So galaxy clusters tend to be more than just a few galaxies, but you can also have small galaxy clusters, but they can accumulate to something like thousands of galaxies. And each of these orangish blobs in this picture is a galaxy that's bound together by gravity into what we call this galaxy cluster. Now, finally, on really large scales, if you really think about the structure of the universe on the largest scales, all of these galaxies and galaxy clusters live in something that looks a little bit like a giant cosmic web. And it kind of helps to look through visualizations of real data. So this is a visualization of data coming from the Sloan Digital Sky Survey, a particular data set from the SDSS. And in this visualization, the positions and some other properties of the galaxies are simulated. And as we kind of fly through this image, you can get a sense of there are places where there are galaxies, and maybe they're sort of connected by what looks like a filamentary structure. And there's also large empty spaces, so something that we call voids. And these are regions of space that don't have any galaxies occupying them. But you can tell from this picture that there's quite a lot of galaxies kind of interconnected in this web. So one of the earliest studies of the existence of dark matter, which you heard about from Rutu's talk, is work that was done in the 1930s by a very eccentric Swiss astronomer named Fritz Zwicky. And this is a picture of the galaxy cluster named the Coma cluster on the left. So here the color is a little bit different from what we were seeing before. These kind of bluish galaxies here are the members, the galaxies that are part of this Coma cluster of galaxies. So he was looking at these galaxies in the Coma cluster, and he found that the speeds of these galaxies seemed to be traveling faster than what was expected. So if you added up the expected mass from all the galaxies here that are emitting light, that couldn't explain how quick the motions and how quick the other galaxies were traveling. So to explain that a little bit more, we can invoke elementary physics that maybe you learned in high school. And there's this picture with a hand and a ball and a string. And if you kind of swing this ball around, there's an equal and opposite force, the force that you put in from your hand, and that's imparted to the ball and the string. And this ball has some mass, and the string is a length of some length r. And then we're saying that the speed is v. And as the ball swings around in a circle, you can imagine the more force you put on it, the faster the ball swings. Now that's a very similar case with the sun rotating around the center of the Milky Way. So the sun is bound by gravity to orbit around the Milky Way. And you can imagine actually that, so instead of the string, now you have the force of gravity, which is holding the sun in these orbits. And the more gravity there is, the faster the sun will rotate. So the more mass there is that exerts that gravitational force, the faster that star will move. So we think that given the measurements of the speeds, for example, of the galaxies measured that Vicky made measurements for in the Coma cluster, that there has to be a lot more mass present than we can actually see by eye. And so we think now that a massive halo of dark matter surrounds all galaxies. And when I say halo, it's kind of referring to this very diffuse blob that surrounds this entire picture here. So not just the light coming from the stars in the galaxy, but something that we cannot see. It doesn't emit light that is surrounding this galaxy. Okay, so the main observations of this has been made, of course, not on our galaxy, but on other galaxies, so nearby galaxies, where what people do is make measurements of how fast the stars are traveling around the center of the galaxy. So this is an illustration of the galaxy, and the distance here on the x-axis, that's the distance from the center of the galaxy. So here it's given in light years, but you can also measure it in any other distance unit. And what's on the y-axis is the speed of that star as it goes around the center of the galaxy. So the data points here are observations from stars, so measurements of the speed of stars as you go out from the center of the galaxy out to the outskirts of the galaxy. And then the blue data points here are measurements of gas, because at some point at large distances, you don't have very many stars to make measurements of speed of, but you can still measure the speed of gas. And here's the model of the expected speed if the mass was only given, if the contributions to the gas only came from the visible light, so the stars that we can see in this image. And since we know that the stars, as we go out to large distances from the center of the galaxy, the light is dropping off. So that means that the mass and the gravitational force is also dropping off. And so that's why this dashed line kind of drops off at large distances from the center of the galaxy. But if instead you have some sort of dark matter that exerts more gravity and thus causes these measurements to have continue to have higher velocities going out to large distances, then you get this solid line, which fits really well to the data. So this is the main piece of evidence that we have to say that dark matter exists. And I can't talk about this without mentioning Vera Rubin, who, along with her collaborators, really pioneered this measurement. So we call these galaxy rotation curves. So that refers to the rotational speed of many different galaxies that they made measurements for. And so this is a picture of Vera Rubin looking through a telescope on the left, and then an actual plot from one of her papers. So this is from 1980. And so now instead of data points, they've drawn a line through all of the measurements, but it's the same type of measurement that I just showed, where the x-axis is the separation from the center of the galaxy, and the y-axis is the speed that's been measured. Okay, so this is a bit experimental because this poll doesn't always work, but if we were in person, I would open the floor to you and ask you, what do you think is the mysterious dark matter in galaxies? So some people have already heard about dark matter, and they are curious about whether maybe they're made up of black holes or some sort of dark star. There's another hypothesis, which is that maybe there's a new type of particle, which it only acts through the gravitational force, but it doesn't emit light. And then that particle is something that we're looking for, but haven't detected yet. And by the way, if you want to join this poll, you can either, you can follow the instructions at the top here. So you can either do it by texting on your phone, or if you have a web browser, you can go to this website and there should be an option there to choose one of these options. And then option C here is that maybe what I've been talking to you about in terms of the gravity, equal and opposite forces, all of that has something wrong with it. So maybe our understanding of general relativity or some way that we formulate all of our calculations involving gravity are somehow wrong. And maybe that means that because these calculations about the rotation speeds are wrong, maybe the dark matter doesn't really exist. It's just that we don't have the right theories to describe what's going on in the universe yet. And then there's another option for if you think it might be something else. So please feel free to take a guess or give your opinion on what you think might comprise the dark matter. And we can come back to this at the end. Yeah, so it should be activated, but it's possible that it won't work. Anyways, okay, so now I'd like to tell you about gravitational lensing, which is again something that Rutu covered in her talk. And then I'll describe it in a slightly different way here. And so gravitational lensing is the phenomenon where the light from a distant galaxy is distorted on its way to us by the intervening mass. So here in this image, there's a really gigantic galaxy cluster that weighs a lot. And so if we think of space-time as being like a sheet of graph paper, and you put something really heavy on that sheet of graph paper, weighing it down, then instead of having these straight lines, so light takes the shortest path to go from point A to point B. So instead of going on that straight path, you have these kind of warped lines in the grid paper. And so the light is then going to follow kind of curved path as it comes from very distant galaxies to where we observe it on Earth. And the more mass there is, so the heavier this thing here is, the more distorted that path is. And we can also look at a little visualization of this. So here's the light traveling from a distant galaxy, passing by something with a lot of mass, and so its path is bent. And so when we see it, we see this kind of distorted image there. So I'll play that one more time. So the original galaxy that emits the light looks like this. But then as we observe it on Earth, it's got this kind of arc pattern to it. So there's some sort of gravitational lensing effect. Okay, so just playing it one more time. All right, and then the whole term lensing, it kind of gives you some sort of impression of an optical effect because it is kind of a focusing or defocusing like effect. And you can actually do a tabletop experiment to make patterns kind of similar to what we see in the universe at home. So here's an example of a tabletop experiment. So on the left here, we have a picture of a candle. So it just looks like a candle with a light. So this is the original source. It's what it looks like to begin with. Now, if you take the stem of a wine glass, and if you have a wine glass with wine in it, first drink the wine and then do the experiment. So if you take the stem of the wine glass and orient it just right, you'll see that the light kind of goes in all angles around the stem of the wine glass. And so what we see as an image is almost like a perfect ring. And this is something that's known as an Einstein ring. And it's very dramatic and visible, and so it's a version of strong lensing. Now, if you kind of shift the wine glass so that it's not perfectly in alignment, but maybe just a little bit out of alignment, you see the image, and there's some sort of distortion effect, but it's not as dramatic as this full Einstein ring. And so typically, this kind of distortion is what we see more commonly when we look at images of galaxies. And because it's kind of a slight distortion, and we only see the image after we see it through the wine glass, we don't know that it looked like this original source on the left. So we need to, there's more information that's needed before we can figure out what that original source looked like, or what caused that, what we call weak lensing. So I said that this happens out there in the universe. We saw a picture similar to this top image in Rutu's talk. So in the foreground, these bright orange blobs, these are galaxies that are part of a galaxy cluster. And you might notice that there are these very visible arcs. So these are very lensed or very stretched images of galaxies that are even more distant than the galaxy cluster in the foreground. And we probably can't really see it by eye, but there are lots of examples of what I'm calling weak gravitational lensing here, where a lot of these galaxy images on the outskirts are probably lensed, or there is some effect on their shapes, but we can't really tell by eye that that's happening. But we can tell for these really dramatic distortions that there's some phenomenon happening there. And also there's an example of the ring. So this is actually a double Einstein ring, where there wasn't just one source being perfectly, like in perfect alignment with the lens, where the light kind of went in all directions around the lens. There's actually two sources. And that means that there are two rings. So you might, it's kind of hard to see the second ring, but it is there. And then this is the first ring. So that's a little bit in analogy with the optical illusion of the candle and the wine glass. So how do we actually make a map of this dark matter? And this image on the left is another representation of the gravitational lensing effect. Here, now we're looking at it face on. So the galaxies in the background have some sort of original shape. And they're traveling through space to us. There's something really heavy weighing down the universe at these positions. So normally there'll be something indicating those locations, like some sort of galaxies or galaxy cluster. But we'll just say this is dominated by dark matter, which is very massive, and it's very heavy. And so the path of the light, as it travels to us, is getting distorted. And this bottom panel is what we see on a two-dimensional projection. This is what we actually would see in the images that we take of the sky when we take snapshots of the sky. And we can see that these galaxies now have shapes that are kind of oriented in a very different way than the original shapes were. So the orientation or alignment of these galaxies tell us, they hold direct information for the amount of matter that had to be present to cause that gravitational lensing effect. And so the idea here is that we take lots and lots of pictures of the sky over a very large region. We measure the shapes of the galaxies. So for example, looking at the shapes of these galaxies, and we make a measurement of how aligned these galaxies are. And we have to do a lot of averaging. So another thing Rutu mentioned was that we have to make measurements of many, many galaxies. And so we will take an average at a given sky location, and then we kind of invert the problem to solve for the mass that had to be there to cause this measured alignment. And then we can make a map of where we think that dark matter is. So this is one of the outputs of that process. So here is a map of dark matter based on the gravitational lensing analysis of data from the Canada, France, Hawaii Telescope Lensing Survey. And so the bright spots here on this image mean that we think that there's a lot of dark matter in those very bright spots. And then if it's relatively dark, that means that we don't think there's a lot of matter there. And you can also make a map of the light. So you can look at the same patch of sky and add up all the light coming from the galaxies that you can see. And this is a representation of what that looks like. So again, you can see there are bright spots and dark spots. So the bright spots are where you have a lot of galaxies and you've added up that light, and it adds up to a lot. And then you can also flip back and forth between the map of the light and the map of the dark. And you can see that there's a few places, maybe I'll show that one more time. You can see that there are a few places here where there's both galaxies and dark matter. There's also some regions where you might have dark matter and not galaxies. And so it's a lot of what we're doing is really understanding what is the relationship between the light and the dark matter. Another thing you can do, so this is actually the same dark matter map, but with a different color scale. So now these bright yellow spots, that's where we think the dark matter is. And you can go to each of these images in the real data, the images that we took with our cameras. And you can see that these regions happen to occupy the same space as all these galaxy clusters. So these 3 pictures here are examples of galaxy clusters. Where these, again, bright orange, yellow blobs are galaxies that are members of the galaxy cluster, and they are gravitationally bound, and they're very massive. Okay, so I'd like to tie it back a little bit into the picture that Rutu was sharing with us, which is that we don't just have dark matter, or just in general matter with gravity. We also have competing forces, the dark matter, which has the gravity, which attracts, and this dark energy, which is some form of energy which causes the universe to undergo an accelerated expansion. And so these 2 forces together are really the important underlying ingredients of our universe. People have also done simulations where they've put in the physics into some sort of computer simulation. And so what they're doing is they're putting in things like dark matter and dark energy, that's here on the left. And then they evolve that simulation from early times to late times meaning what the universe looks like today. So kind of evolving through the history of the universe. And if we play this one more time, there's also examples of simulations where they only put in dark matter. And so that's an example on the right here. And the important thing here is that these simulations give you a pretty good idea of the structure. So what all of the galaxies look like. If you kind of compare to the fly-through visualization that we saw at the very beginning, you can compare the real observations of the galaxies to the simulations. And it turns out that the simulation on the left is a much better representation of what we actually observe in the universe. And so we think that really there has to be these 2 components, dark matter and dark energy, not just dark matter. Okay, so there's a few experiments today that are doing analyses, some of which are being wrapped up now and soon we'll get results. And these are the 3 that I'd like to talk about, although I actually won't talk about 2 of them. One is the kilodegree survey that's based in Chile and is mostly comprised of people based in Europe, but also some in Canada and Australia. There's also the Hyper-C Prime-Cam survey. This is a telescope in Hawaii and is run primarily by Japan along with Princeton University. And finally, there's the survey that you've already heard about called the Dark Energy Survey, which several of us are members of. And so that's the one which I'd like to very briefly talk about some early results from. And some more beautiful pictures. I think Rutu already showed quite a few, so I'll go very quickly through these. And another slightly slightly more recent collaboration photo from DES. And finally, during a pandemic, we look like this. So our last collaboration meeting was on Zoom. So we haven't been able to see each other in person for quite some time. And finally, here is one of the results from the dark energy survey. So each of these small patches show the mass map coming from a particular data release from the dark energy survey. The first one is from an early data set, and then the middle one is from a data set that was released a few years ago. And finally, this large map, that's made from the analysis of the shapes of more than 100 million galaxies. And that is actually not published yet, but it will be published, submitted in like pretty soon, I would say maybe within a few months. And so please stay tuned. I think we're learning a lot about dark energy and dark matter from maps like this and from other sorts of measurements of the structure. Okay, so I'd like to quickly talk about a few future experiments. So one is the Veracity Rubin Observatory, which is an 8.4 meter telescope based in Chile. And this will survey the whole available sky. So it's in the south, so not all of the sky is visible from the south, but it will do that every few nights. It's supposed to come online pretty soon, and then it's going to conduct a 10-year survey, which will do a lot of the kinds of gravitational lensing measurements that I've talked about today. There's the Dark Energy Science Collaboration, which is going to work to analyze all the data. And it's not just going to be about looking for the dark matter and dark energy, but also look at all the visible matter. There will be lots and lots of stars and galaxies coming from the Rubin Observatory. And it'll be, I think, 20 terabytes of raw data per night coming from this telescope. Now, from the ground, we have some distortions to the images of the sky, primarily coming from the atmosphere. So the atmosphere tends to blur out the images that we receive. Now, if you go to space, you can really, you don't have to deal with the atmosphere. And so you can really resolve distant galaxies. And if you look closely here in the center, there's an example of an Einstein ring. So the last thing I'd like to tell you about is a telescope called the Nancy Grace Roman Space Telescope. It used to be called the Wide Field Infrared Survey Telescope, and it was recently renamed for the first chief of astronomy in the Office of Space Science. And this is one of the successors to the Hubble Space Telescope. So it's Hubble-sized in terms of telescope power and resolution, but it's 100 times the field of view. And the idea is, again, that we want to investigate dark energy and dark matter, but also Roman will be able to look for planets outside of our solar system and much more. So this is all very exciting. Okay, so I'd like to conclude by giving you some takeaway points. So there's some strong evidence for the existence of dark matter. This is a kind of invisible matter that doesn't emit light, but does exert a gravitational force. We can't see the dark matter, but it contains a lot of mass. And that mass distorts the light from distant galaxies, and that's this gravitational lensing effect. So you can invert the problem to understand what is the mass that caused that lensing effect. And then you can make a map kind of like this. And finally, we're expecting a lot of exciting new data from upcoming telescopes that are still being constructed. And this is going to tell us much more about the dark elements of our universe. So finally, thank you, and I will take questions.
Thank you so much, Amy. That was very interesting. And we already have some questions in the chat. So let's see. Bernardita says, do we actually observe 21 centimeter wavelength, or does the wave stretch when it reaches the Earth?
Sorry, could you say that one more time?
I think she's talking about 21 centimeter wavelength. I think she's asking, do we actually observe 21 centimeter wavelength when it reaches our detectors, or does it actually stretch when it reaches the Earth. I guess maybe she's talking about if she's redshifted or.
Right. Yeah. So there's for that's coming from gas. So there are these hydrogen in the gas, and then so on Earth, if we were to make measurements of the spectrum of the hydrogen, that would come at a particular wavelength, and then it gets stretched to 21 centimeters.
All right.
There's some. It's kind of like a Doppler effect. I don't think we talked about it in either of our talks, but as the light is coming to us, there's like this redshifting effect, which is like a Doppler effect, and so it changes the wavelength from to a longer wavelength, and so you get certain things. Kind of like actually with the cosmic microwave background. So those photons were emitted at the very early times of the universe. And so by the time we reach those photons, the wavelengths have been stretched to really long wavelengths. So it's a sort of similar thing with the hydrogen.
All right, thanks. We have a few more questions. So actually, the next question has to do with the redshift. From Fred, it says, light travels so far and long to reach us. How can we be sure redshift is only due to speed? How would the theory change if there are other reasons for redshift?
That's a complicated question because the theory, if we understand the physics the way that we do, it has a very particular prediction for that redshift. So how things would be stretched as a function of time. And then we match that model with the observations, and that tells us about the expansion or the particular, it gives us an interpretation of what causes that redshift. I think there could be, well, certainly there are different, slightly different models for the expansion of the universe that might predict slightly different redshifts. And so there is some understood differences in those models, but they all, I mean, on the big picture is all the same in the sense that they all contain roughly 70% dark matter and roughly 30%, 70% dark energy, 30% dark matter, something like that.
Yes, okay. All right, thanks. Our next question is, which gravitational lensing is more important for cosmology, weak or strong?
They're both important. So the strong lensing can be used for other purposes, which I didn't have time to talk about today. One purpose is actually to measure the expansion of the universe. And that's actually quite important because it's one of the main parameters, like the main ingredients of our overall model, is to understand that expansion. And the weak lensing that I talked about today actually does not really constrain that expansion very well. And so they're very complementary in that sense. But I would say strong lensing is so rare that it's just a very different kind of measurement. There's not very many places on the sky where you get that perfect alignment and you're able to measure or do these kinds of analyses on those kinds of systems. But it is, it gives a complementary view of the underlying physics. I'm not sure I would say one is more important than the other, but that they give different perspectives of what's going on.
Yes, I thought you were gonna say weak lensing because Amy is the weak lensing, one of the leaders of the weak lensing working group in the dark energy survey. Although you're right, they're complementary, as you said. And now that we're gonna have the surveys like the Rubin Observatory, where we're gonna have more strong lenses, occurrences, then it's going to be an important component as well of cosmology. So yes, thanks. And then we have another very interesting question from Robert again. And Robert asked, how close are we to resolving the discrepancy in different Hubble parameter measurements? Ooh.
Good question. I don't know. I think there's a lot of continued analysis of the data. The main thing that people wonder right now, so for the Hubble constant, that's actually a question that strong lensing can place information on. So that's what I was talking about when I said strong lens. There's actually some aspect of the measurement where you can directly constrain the expansion of the universe. And so I think the main way to making a clearer picture of what's really going on for the discrepancy. So there's different measurements at like nearby. So based on nearby calibrations of exploding stars, and this measurement predicts a different expansion rate than measurements of the cosmic microwave background. But that cosmic microwave background is coming, that information comes from really like when the universe was really young. And so they're kind of giving us snapshots of the universe at different stages of its history. So there is a question there. I think the main question all of us are trying to answer is whether that discrepancy or that difference is because of some real physics that happens between when the CMB light was emitted and the more closer to us measurements that we're making, or whether there's some issue with the actual measurements, whether there's some analysis error, or for example, maybe we didn't get the calibration of our detectors on the Hubble Space Telescope correct. I mean, there are different ways in which the measurements maybe could have some sort of unknown error. Although people have done this analysis very carefully and have done extensive checks on the kinds of measurements. So I would say that the jury is still out. And I would be hopeful that in the next few years, we get some sort of better understanding of that just based on the additional measurements we're getting from new experiments, like some of the ones I mentioned, and just getting better ideas of what are the things that can go wrong in the analyses. And also people providing interesting theories for aspects of the physics that can maybe create this kind of effect.
Yes, absolutely. We have to get creative with the theories, and at the same time, we need better data. That's the key. That's what we're going to get with the future observatories like Rubin or Nancy Roman Space Telescope, as you mentioned. And we need a better control of the errors, as you mentioned. Some of us actually, I wrote my thesis on understanding errors in weak lensing technique. So you can spend your whole PhD thinking about this as well. All right, thank you so much. I think we reached the end of our emission today, and I would like to thank Dr. Choi and Dr. Das one more time for their time, and I would like to thank the audience. Please follow us on social media, on Twitter and on Facebook, and please keep an eye for our events. Thank you so much for coming to Astronomy on Tap St. Louis tonight.
Thanks.
Thanks, everyone. Bye-bye.
Bye.
Bye.